Hi everyone, welcome to another video by Cheenta. I am Rajdeep, and in today's video, we'll look at the concept of a minimal polynomial. It's a very fundamental concept in especially what comes out to be algebraic number theory at a higher level, but also just the basic algebraic theory of polynomials. We'll do so using a problem from the CMI 2012 B.Sc entrance, where there needs to be an explicit calculation of a minimal polynomial, and that will highlight a few things. At the end of the solution, I will add a few more notes so that when you finish watching the video, you have a greater appreciation of how numbers work. So let's get into it. So the problem is from the CMI B.Sc entrance of 2012. This is problem B1. This is one of the years where there was an objective section. It was an entirely subjective paper. This is from part B. Let's look at what the problem says. Part A says, find a polynomial px with real coefficients such that p of root 2 plus I is equal to 0. Okay. Part B says, find a polynomial qx with rational coefficients and having the smallest possible degree such that q of root 2 plus I is equal to 0. Show that any other polynomial with rational coefficients and having root 2 plus I as a root has qx as a factor. Alright? So for part 1, there is a clear issue, which is you can't define a polynomial as x minus root 2 plus I is equal to 0. This does not work because this is not a real polynomial. This is a complex number. For those of you who don't know what I is kind of a symbol we have made up which has the algebraic property that when we square it, it's a number which when we square, we get minus 1. If this seems absurd, at the end of this solution, I'll show you that kind of, if this is absurd, then so is root 2. And we'll get to that by the end of it. It's a very interesting philosophical digression that I personally love a lot, but we'll get into it. So this does not work, x minus root 2 plus I. So what do we do now? If you recall, there's a result that's true for real polynomials, which is if px is a real polynomial, there's a result. This is not very hard actually to prove. And in one of my previous videos in this series, I have proved it. If px is a real polynomial, which is a polynomial with real number coefficients, and z is a complex root of px, so is its complex conjugate z bar. What does this mean for us? That if px was a polynomial, a real one, which had root 2 plus I as 0, it would also have root 2 minus I as 0. So at the very least, our polynomial is x minus root 2 plus I times x minus root 2 minus I. You need both of these as roots, so I'll just throw in the minimal amount, which will give me, if I just do this properly, it will give me x minus root 2 whole square minus I square. And this is equal to x square minus 2 root 2x plus 3, because I square is equal to minus 1. Very nice. And this is a real polynomial. Of course, both of these are real numbers. And root 2 plus I is the root. So that solves our first part. Let's look at the second part. And now we want rational coefficients. If instead of this 2 root 2, we had a rational number, this would have been sufficient, but it's not. So what do we do now? One strategy is to square this. So how do we get rational stuff? In particular, we want this root 2 to go away. One standard way is to note that whatever x satisfies this will satisfy x squared plus 3 is equal to 2 root 2x. Here's a standard thing we do. We isolate the part that we don't want and we square it so that the root 2 goes away. To get that, x squared plus 3 whole square is equal to 8x squared. And if I now rearrange, I'll get p of x is equal to x square plus 3 whole square minus 8x square is a rational polynomial. This is not very hard to see if you square it. This is a 4-degree polynomial, and it is x to the 4 plus 6x square plus 9 minus 8x square, which is nothing but x to the 4 minus 2x square plus 9. So now this is a polynomial which is rational, and it satisfies and it has root 2 plus I as a root. So yeah. But remember that you also want it to be of the smallest possible degree, right? So how do we verify that this is the smallest one? In some way, we should have some confidence. We have not done any wasteful movement. We have not done anything that would have incurred an extra root. We've only done the most natural thing, so there should be some confidence that what we have found is the minimal one. One thing is clear, is that the minimal polynomial in this case are the rational polynomial of smallest degree, which has root 2 plus I as 0, is not of degree 2. Because if it was of degree 2, it would be this, right? Because if root 2 plus I is a root 2 minus I is a root. And then the polynomial is a multiple of this. So that can't happen. Which means all we have to verify is that a cubic polynomial can't have root 2 plus I as a 0. But if it did, it would have to look like x square. Obviously, it would need to have root 2 minus I as a 0 as well. So this part already gets multiplied. And it has one root left. So our polynomial, cubic polynomial, if it were to satisfy this the condition that root 2 plus I is 0, would have to look like this. Or well, we can write it like this. This would have been the only possible candidate, where R is some complex number. Now, in fact, it would have to be a real number, because otherwise you would need the conjugate as well. So R is a real number. The only issue is that this cannot be a rational polynomial. Why? Because then we'd want 3R to be rational, which is the constant term, which in particular implies that R is rational. And we'd also need 2 root 2 minus R to be rational, right? Because that's a coefficient of x square. So, but if R is rational, then 2 root 2 minus R can't be rational. Because if it was rational, then if I add plus R, which is a rational number, it would imply that 2 root 2 is a rational number, which implies that root 2 is a rational number. Can't happen. So cubics are out, quadratics are obviously out, and linear polynomials can't happen. Because root 2 plus I is not a rational number. It's not even a real number. So this proves that this is in fact the minimal polynomial, so as to speak. There's still a little bit more left, to which to show that any other polynomial with rational coefficients and having root 2 plus I as a root has qx as a factor. This furthers our notion of this one being the minimal polynomial of root 2 plus I. It is every other polynomial will have this qx, this polynomial, as a factor. In some way, this polynomial generates all the other ones that have root 2 plus I as 0. How do we prove this? Simple. We appeal to the Euclidean algorithm for polynomials. If fx is another polynomial such that f of root 2 plus I is 0, I will simply divide it with our polynomial px. Right? And I'll get some remainder and some quotient. So I'll get f of x is equal to qx, rather, let me do px into qx, where qx is the quotient, plus rx, where critically the degree of r is less than the degree of p, which is 4. Now f of root 2 plus I is 0. So if I plug in root 2 plus I in this part, f of root 2 plus I is p of root 2 plus I times q of root 2 plus I plus r of root 2 plus I. Right? By definition, f of root 2 plus I is 0. I have already constructed p in such a way that this is 0, which implies that r of root 2 plus I is 0. Which can't happen because p is the smallest polynomial, by which I mean the polynomial with the smallest degree, which has root 2 plus I as root. And degree of r is less than degree of p. So this is a contradiction. Hence, the only way this could work is if r is the 0 polynomial, right? And that solves the problem for us. I do want to say a few things. How do we generally do this? And why is it that, what is special about the minimal polynomial? If you actually check what the roots of this polynomial that we've drawn up are, they would turn out to be root 2 plus I, root 2 minus I, minus root 2 plus I, and minus root 2 minus I. It's a very special set. And in some ways, if we make another check, which I'll not get into, it can be shown that this polynomial is what we call irreducible. I have a small digression to make here, which is what I referred to in the beginning. A lot of people take up issue with the fact that we define I to be some imaginary number, which when you square is minus 1. In particular, we define it as the guy that solves x squared plus 1 is equal to 0. But if you think about it, that's all we've done from the beginning. There's all the things that we get naturally are the natural numbers. We get 1, 2, 3, 4 and everything. That's the natural numbers. Best case, you get 0 as well. How do you get the negative numbers? You ask the question, what solves x plus 1 is equal to 0? That is how you get minus 1. That is the definition of minus 1. So we make up this symbol minus 1 and we use it as the thing that when you add to 1, you get 0. That's what the definition of minus 1 is. And what about half? Half is also just a symbol. Like I'm thinking of purely in like a symbolic way, philosophical way rather. Half, what is half? Half is just a symbol that means the thing that when I multiply it by 2, I get 1. That's just a symbol. We've been doing this from the beginning. Somehow we've accepted half and minus 1 as reasonable constructs. But the moment I ask, what about the thing that when I square it, it becomes minus 1? Suddenly a lot of people take issue with that. You shouldn't. Even root 2 for that matter. Root 2, all of these you could say are natural. Root 2 is incredibly unnatural. It's an irrational number. It has no nice decimal expansion. It's an infinite thing. It's very unnatural. And yet people accept it. There's no difference between root 2 and I for that matter. We define root 2 to be the thing when I square it, I get 2. That's what the definition of root 2 is. The only thing is that if this is how I define root 2, there's no difference between minus root 2 and root 2. Because minus root 2 also does this, right? So it's really just a matter of symbols. This is what is called a conjugate in the what's called the Galois sense. I don't get into the exactness of this thing, but the point is that x squared minus 2 is, well, the minimal polynomial of root 2, but it's also the defining polynomial of root 2. There is no root 2 without this polynomial. But minus root 2 also satisfies it. So in a way, for root 2 plus I, or any algebraic integer, which is any number which can be defined via polynomials, the minimal polynomial is just constructed by throwing in all of the things which are the brothers of the number. Root 2 plus I does not exist without minus root 2 plus I, minus root 2 minus I, and minus root 2 minus I. The moment you define root 2 plus I to be anything, you'd have to define it in this way. So of course you could define it as x minus root 2 plus, it's the thing that solves this. But it has no natural sense to us. What's natural to us is rational numbers or integers. And so, yeah, root 2 plus I is the thing that solves x squared minus x to the 4 minus 2x squared plus 9 is equal to 0. And the moment you define it as that, you get all of its other brothers. And so, yeah, that is kind of the point I wanted to make, that the minimal polynomial is a very special thing. It kind of defines these numbers. So yeah, that is all I wanted to say for this video. I hope you enjoyed, and I hope you took away something meaningful from it. Thank you very much for watching. Bye-bye.